Yeah, so just quickly want to recap what Morrow has illustrated. So basically, what Morrow has shown is that you can write generic rules and without even considering the complication of distribution. Once those rules are written, you can use Julius graph engine to automatically distribute that to multiple workers without any modification code change. That is tremendously beneficial and save a lot of time. Just imagine how you can do this in a traditional programming way. If you write a complicated function that need distribution, that can require major engineering effort to make it run fast and optimally in the distributed setting. So um, again, like if you have any more questions, please feel free to ask on the Pigeonhole link. We're going to answer it opportunistically, and also hopefully we'll leave plenty of questions in the end for Q&A. So in this section of the workshop, I'm just going to show another example, which shows how large-scale graph computation can be handled and distributed. So I'm going to share my screen. Oh, sorry, I'm sharing the wrong screen. Okay, so hopefully the right screen is shared. All right, so here we're just, so far we have been showing some examples in machine learning, in data processing. In this example, I want to really quickly illustrate what is a large computation looks like using our Julius graph engine. So in this case, we are showing a application that price a large book of derivative trades. So it's 100,000 of derivative trades, and the entire graph is like more than a million nodes large. As you can see that the graph is too large to fit into a single page, but we allow easy navigation for the user to drill down to different parts of the graph and visualize every intermediate results if the developer want to see. So in this case, for example, you can, again, like even with a million nodes, you can easily trace the various intermediate results. And again, the distribution is handled generically. You haven't done anything special just to distribute this particular problem. All of this distribution capability and lineage, like visibility, UI, all of these are generic, applied to any problem you can code up using root DSL and atoms. In this case, for example, we're using 4 different workers to distribute this relatively large graph. And you can see the distribution is highly optimal because in this case, you can see that there's an entire block of dependent nodes that are all allocated to a same worker. So this minimizes the data transfer between different workers. So that by clustering the relevant node in the same work actually dramatically improve the performance. The reason we can do this type of optimization is also enabled by the root DSL because root DSL give us very easy way to name a particular node in the graph. Therefore, we can distribute the graph at much bigger chunks instead of some other platform have to distribute the node one by one, which turned out to be much less efficient. So this is one example of handling large computation. By actually, like a million node graph is by no means reaching our limitation. So we can routinely handle graph as large as hundreds of millions of nodes. That is not a problem at all. So really want to emphasize that the solution is generic and can scale up to the enterprise level. So the last example I probably wouldn't spend too much time on, but just quickly walk through the main conclusion is that oftentimes when you are building a machine learning model or actually building any system, um, so to track your different configuration and experimentation is a tedious task. So sometimes you may have a machine learning model that you happen to train well and get a very good result. And a few days later, certain data input change, a certain configuration change, you can no longer regenerate that good result. This is often a very common problem in ML ops. So here we're going to illustrate how Julius can help solve this like a tedious ML ops problem uh, by taking advantage the generic capability of reproduce and easily change the system. So in order to fully persist a distributed enterprise system, you have to do the following three things. So the entire runtime environment, including like hardware, like OS version, software library, all of this has to be like has to be reproduced, and then the input data has to be persist, and also entire code base parameter and configuration of the entire system has to be captured. So the first item, this is well solved by using Docker containers. That become a standard way of having a standard environment hardware OS. So that is well solved. However, the input data and the entire code base and configuration still remain hugely complex thing to capture, especially for when you have a system running on multiple machines and spanning a large number of components. So in this case, like when we take advantage of the graph computing platform in Julius, we make the entire process super easy. This is pretty much the same code as Mauro showed in the distributed machine learning use case. And we can see that once the user developer finished his development and get reasonable results, for example, if he is happy with this part of the results, what he can easily do is that he can create another cluster, a fresh environment that has nothing to do with the environment the developer used for coding. And from this fresh environment, he can easily send the same commands, send the same rules and items to this fresh cluster and turn on the recording on the server side. So once the server side recording is complete, so here you let's see, show. Yeah, so once the server side, here we create a fresh cluster and we turn on the recording on the server side, then you send the same command to this new cluster, which you want to reproduce. And then we can take a serialized data structure of all the things that are happening on the server side that include your entire configuration environment, your all the things you need to recreate that distributed graph. Then you can persist this record in AWS or some other storage. Then later on, if you want to recreate this environment, you can just replay this record, and then you can see that in the end, you exactly recreate the entire distributed machine learning pipeline with identical results. So this is how easy we can help the developers to manage their machine learning experimentations. So whenever they have a good results, you want to persist, it just take a few lines of code to record it on an entirely brand new environment. And if you ever want to retrieve and recover that environment, you just replay it and it becomes instantaneously available and to be identical copy of your previous configurations. So this is the last example I want to share. So now let's open it up for Q&A. I'm going to add my colleagues to the screen, and if you have any questions, please feel free to ask. So let's see if there's any questions coming through from Pigeonhole. So if there are no new questions, I'll probably just go through some of the old questions to make sure we have adequately answered them through the pigeonhole. Yeah, so there is a question about how can we catch the best model. One of them using either for batch or streaming prediction. So we just showed that how easy it is to take a record and replay that record. It works for both batch and streaming mode. Yeah, there is a question about what is the advantage of using a graph-based approach compared to a conventional one for machine learning problem? Yeah, so this all goes back to the stellar advantage. So if you want scalability, transparency, explainability, lineage, low code, reproducibility, and adaptability, that's really you should look at a graph-based solution. The conventional programming language, you have to solve this problem on your own. So
I think below there are some questions with no answers.
Yes, there's a question about training in Python. Why did we train in Python and not in Julia? Of course, you can train in Julia. The Python example was to show the interfacing capabilities. And of course, Python is widely used for machine learning, so that's why we chose this language. In my case, it was not distributed, but as Mauro shown, you can also distribute a machine learning training process.
yep, so certainly you can use Julia version as well. So there's a question about about pre-compilation overhead in graph computing for the whole pipeline because of Julia pre-compilation. So yeah, this is a good question. So it's true that we do have this pre-compilation overhead. So the first time you run the graph, calculation tend to be a bit slower. But the things is graph are geared towards like heavy computation, that a little overhead for pre-computation is not a big deal. If you look at end-to-end grand scheme of things. Yeah, there are a lot of questions we probably can't answer live online. We'll try to type in our answer in the pigeonhole in the chat room. So I don't know if there's more questions coming through. Yeah, there's a new question. What do you see as your current biggest challenge as in using or developing this computational framework? Right, so that is actually a very good question. So I would say, maybe like Mauro or Melina can share your thoughts. I would say that graph computing is a very new concept. Not too many developers are familiar with it. So I would say probably require a bit learning and education to get used to the way of thinking. Because if you think in the graph construct in the graph manner, is different from thinking in terms of traditional imperative function way of programming. So I would say that that changing in your thinking about computation is probably something we need to work more on to get the developer comfortable and see the benefits of graph computing.
Yeah, indeed, I agree. This is a difficulty that may arise, but you can deal with it by training, by seeing some examples. Especially this kind of tutorials are really helpful for doing this.
Yeah, there's a new question: how to deal with errors in certain node if they occur after data upload or new execution, maybe new parameter. Yeah, this is a great question. So we didn't show this part of the functionality, but we support a generic trigger. So you can define a generic trigger mechanism on your graph that can monitor any of these runtime exceptions or runtime conditions. So it can be data error or certain nodes running too slow or data arrive not in time. So once you have the trigger attached to your graph, whenever this condition happen, you can define your handler so that depending on how your handler is written, you can do different things. So for example, you can ignore the error, you can page a developer, or you can try to roll the previous value forward. All of these different strategies you can code in your trigger handler. So this is a very generic way of handling errors or any kind of runtime exceptions you may encounter during the graph computation. It tends to be very important for running like a large production system because you cannot possibly like leave it to human intervention every time this condition occurs. So the next question is there any introductory published books for graph computing with Julia? I'm not aware of any, but yeah, maybe that is a good suggestion. Probably someone should write one. So it looks like there's more question coming. Let's wait a few more minutes. There will be a presentation from our CEO James Lee in the main conference. So certainly you're welcome to join that presentation about the Julius technologies as well. Okay, so I think like probably we can conclude this workshop. Let me just at the end share some of the links that will be useful for people to find relevant materials. Just one. Yeah, I'm going to share my my screen with a couple of last page. Oh, there's a new question. Okay, let's answer this new question. Regarding persistent, that is, thanks for the comment. Oh, great. Yeah, it's a comment, not a question. I appreciate your nice comment. So we're going to share a screen with a few links so that if you want to find the material afterwards, you can have the link in the video. Right, so here on the screen, we're showing the link to sign up for our developer environment and also a few other resources that you please feel free to browse. And also the second page is our like blog pages and our email. If you want to reach out to us, ask questions, please do so using the email or like leave a comment in our LinkedIn pages. I think we can conclude this workshop. Thank you very much for joining and look forward to hear from you.
Bye-bye. Thank you very much.
Bye.
Bye-bye.
Thanks for joining.